Hi, hello, welcome to a ramble with moi. Looking at the department's paper 1 from November 2022, question 7.3 today. The tangent to g of x is equal to ax cubed plus 3x squared plus bx plus c has a minimum gradient at the point -1, -7. For which values of x will g be concave up? Okay, so the tangent to this function, which is a cubic function, so okay, we don't know whether a is positive or negative, so we don't know whether it's a cubic that does that or if it's a cubic that does that. But yeah, maybe not so material for now. What we do know is that at the point -1, -7, let's say maybe, oh, that's not going to be up there. Okay, let's say it's some random point over here. We are told that the gradient is the lowest that it could ever be on this curve, which is interesting. So that makes me feel like yeah, I don't know what to make of that information. I'm struggling to visualize it, but maybe once we arrive at an answer, it'll make sense to me. So, and then the question is, for what values of x will g be concave up? Okay, so I have no idea how all these dots are going to connect, but you know, when you talk about a minimum of anything, I think optimization. So if I can get an expression for the gradient of g at any point, and then figure out, okay, where is that expression at its lowest, which we are actually told. We're told that it happens when x is equal to -1, but by knowing that, maybe I can figure out what a and b are, and then come back here to figure out, okay, the second derivative of g, which will then help me figure out concavity. So that's a very rough kind of plan. So let's see how far we can get. So I'm going to start by figuring out, okay, the gradient function, which will be 3ax squared plus 6x plus b, right? So the gradient function is, as expected, a quadratic function. So it is a parabola. So, you know, it's either going to be a parabola that's like this or like this. But because the question is asking, is saying that there is a point where the gradient is at a minimum, right? So then this wouldn't make sense because there is no minimum, right? This function goes infinitely that way, goes infinitely that way. So the gradient values can get more and more negative, right? More and more negative. So this wouldn't make sense, whereas this would make more sense because at this point over here, the gradient function outputs its lowest value, and that means that whatever the x value is here on this graph, this will be the point where the x value, where the tangent has the smallest gradient you can possibly have. I hope that makes sense. So this over here, the fact that this exists disqualifies this as a possibility. This is the only parabola that would make sense as a representation of the gradient function. So we are told that, oh no, we are told, we are told that, okay, this over here, the lowest gradient value occurs when x is equal to -1, right? And we don't know what the gradient is at that point, but we know that it's the smallest that it can ever be for this curve. Okay, so that's one piece of information that we have. So how we can use that to set up an equation to solve for a and b is we can say that the turning point of this curve occurs when x is equal to -1. The gradient of this graph is okay, the turning point of this parabola is at x is equal to -1. I think I've explained how sufficiently, hopefully, how I've arrived at that. So we know that the x coordinate of a turning point is given by, if you have mx squared plus nx plus q, then the turning point is given, the x coordinate of the turning point is given by minus n over 2m, i.e. minus whatever the coordinate of the coefficient of x is over 2 times whatever the coordinate of x squared is, right? So in this case, it will be minus the coordinate of x. Why did you say coordinate? The coefficient of x, which is +6, divided by 2 times the coefficient of x squared, which is 3a, right? So that will be minus 6 over 6a, and that simplifies to minus 1 over a, right? And we know that that x coordinate is -1, so we can solve for a. So that'll be -1 is equal to minus 1 over a, times by a on both sides. So we have minus a is equal to -1, and therefore a is just equal to 1. That worked out quite neatly. Okay, right? So now we have the value of a. We just need to figure out the value of b. Oh, there's also a c. Oh my goodness, there's a c in the mix, y'all. Maybe we don't need to figure out c. Because let's just see here. To figure out concavity, we'll have to find the second derivative, which will be 6ax plus 6. Yeah, so just by knowing a, we are fine. We don't need to figure out anything else, really. So we now know that a is just 1. So this is 6x plus 6. So then the curve will be concave up. Concave up is this, and it occurs when the output of the second derivative is positive, right? So we are looking for the places where 6x plus 6 is greater than 0. So we solve this inequality, minus 6 on both sides, divide by 6 on both sides. So the curve will be concave up when x is greater than -1. So that then tells us that our curve, so we have -1, -7 somewhere on the curve, and it's concave up after -1, so it's going to be like this. So it looks like that. which, I mean, we could also tell from finding out that a is positive 1, so this is a positive term. Well, it has a positive coefficient, so then we know that our curve does in fact go like this instead of going like that. Is that it? I feel like I've underutilized information here. Let me just go over my reasoning again, because this was very weird for me. The tangent to this curve has a minimum gradient at the point -1, -7. Right. So I mean, okay. So it won't be kind of using knowledge we have from the future, we know that our curve looks like this. So, well, and also I just maybe want to disqualify the other curve up front, the other alternative. So say we didn't know that it does in fact go like this, if we thought maybe it might go like that. With this curve, we won't have a tangent that has a minimum gradient, because if you just look at this part of the cubic curve, your tangent is going to be like this, right? It's going to be a negative something. And then the further down we go, is it not getting steeper and steeper? Is it not becoming more and more negative? Is that necessarily the case? So if, this is really rambling now. So just say hypothetically we had, oh no, it's going one that looks like that. So your tangent here will be like that, and then if we go a bit further down, it becomes a bit steeper, the gradient becomes more negative, and like that. Yeah, I think there might be a way to show that. So let me hide this ruler for now. So basically what I'm trying to say is, if I have a function, a cubic function, that looks like this, okay, and specifically we are interested in the case where, a is bigger than 0, a is positive, so then this is a negative number, right? So that the curve looks something like that. So then the first derivative will be negative 3ax squared plus 2bx plus c. So that, because this is positive, this will be negative, so this will be a negative something x squared. So the parabola representing h prime will be, something like that, which tells us that the gradient of any tangent to this curve, right? The gradient of any tangent, so if you choose any point anywhere on that curve and you draw the tangent, there will be a maximum gradient, right? There will be a certain gradient value that we can't go beyond. And that kind of makes sense to me, because the positive gradients, the tangents will only have positive gradients if you choose a point somewhere here in the curve, right? Where the curve, generally it's increasing, right? So then if you pick any point in this little segment, then you will get a tangent with a positive gradient. And this is a closed range, so it'll only get so positive, right? The rest of the time, the tangents will have negative gradients, and according to this depiction of the gradient values, as your x decreases, your gradients for your tangents are also just going to get smaller and smaller and smaller. They're going to get more and more negative. And likewise here, as your x increases, then your gradients are also just becoming more and more negative. So there wouldn't be a minimum gradient, because for whatever minimum you think you found, I can just look at the next x value and it will have an even more negative gradient. I hope that makes sense. So so pretty much basically from the mention of there being a minimum gradient, we already knew that it would have to be a curve like this, because it would have to be a cubic curve where the decreasing bit is limited. Okay, anyway, so then from there, having been told that our minimum gradient occurs here, minimum then triggered optimization. So I took the function that describes the gradient of this curve at any point, or rather the gradient of the tangent at any point on this curve, and that function looked like this. So 3ax squared plus 6x plus b. Okay, that's the first derivative of this guy. This is the gradient function for g. Okay, and only here did I eliminate. Okay, yeah. But anyway, yes, so the idea here was that, okay, this parabola that describes the gradient of this guy, it can't look like this, because then we wouldn't have a minimum value, right? So it has to look like this, because then we get a minimum value here, and in fact the question tells us that the gradient of the tangent is at a minimum when x is equal to -1. So that is where our parabola is at its lowest, is when x is equal to -1. But then we use that fact to kind of work backwards to figure out what a is, because we know that the turning point of a parabola is given by negative this guy over 2 times this guy, right? So that is, when it's simplified, it becomes minus 6 over 6a. Oh my goodness. And then that simplifies to -1 over a, but we know the x-coordinate of the turning point is -1, so we could then see that a is equal to 1. But now the question is only asking for which values of x will g be concave up, which is so this was a terrible diagram. In fact, let me just correct it, because what's actually happening is that we actually need this to move a bit this way. So our curve is doing something like that, where the minimum gradient is happening somewhere here at -1, -7. That's where the gradient of the tangent will be the smallest it can be. Okay, right. Anyway, so then the graph is concave up. We're trying to figure out which x values it's concave up for. We do that by finding the second derivative of this guy. So that would be 6ax plus 6. And we want to know, and since we know that a is 1, we just substitute the 1 in there, so we get this expression. And we want to know when this is positive, because that's when the graph will be concave up. And we solved that, and we found that it's when x is greater than -1, which kind of makes sense intuitively. Yeah, it kind of makes sense, because essentially then this is the point of inflection for this curve. So it's almost like, if you look at the points leading up to this guy, the gradient was getting more and more and more negative, and it became the most negative here, and then from here the graph starts working towards picking up again, so this gradient is becoming less and less negative until it's eventually zero here. Anyway, wow, let's see if this is in fact correct. 7.3, yes, we agree. Now let's look at the approach. This is like a three pages of possible solutions. Okay, so let's dive in and see how they've gone about it. Okay. Okay, so what they've done as a first approach, they just straight away found the second derivative of g, which was 6ax plus 6. They then substituted the -1, the x is equal to -1, and found that g double prime is equal to 0 when x is equal to -1, and therefore there's a point of inflection. Oh, no, sorry. That's not what they jumped to. Sorry, that's not what they jumped to. They then solved for a. Wait, why is it equal to 0? I guess they made it equal to 0 because I guess at the point of inflection, that's when you have the minimum or the maximum gradient for a tangent. I don't know, that's news to me. It makes sense, but yeah. Okay, so I'm not sure about that first solution. As in, like, it makes sense to me, but it's definitely not something I would have thought of off the top of my head. But yeah. Yeah, okay. All of these alternative solutions are just kind of hinting at the idea that this minimum gradient at this point is telling us that this is the point of inflection for this curve. And then you kind of have to reason about, well, is it a curve that looks like this, or is it a curve that looks the other way? So it's all just kind of coming to, it's kind of going in the same circle. Anyway, wow, this was an extended ramble, but as usual, I hope it was helpful to kind of dive into this together. And yeah, I'll see you another time for another ramble.